Okay, we are on time. Stella,
Yes.
do you think we can start now, or there are more people
Yeah.
still coming up?
Well, I guess there will be more people coming up, but yeah, maybe you can wait 1 or 2 minutes.
Okay, let's wait a couple of minutes and then we'll get started.
Okay, I think we can start.
Okay, hello everyone. Welcome to another episode of FSI Seminar Series. Unfortunately, I could not be in person today. And then before we begin, I would like to thank today's speaker, Dr. Michael Kinzel, for accepting our last minute invitation. Thank you so much. And today, he'll be talking about the aerodynamics on the Titan environment, predicting Dragonfly lander operations on Earth. A little more about our presenter today. Dr. Michael Kinzel is an assistant professor at UCF Mechanical and Aerospace Engineering Department. He runs the computational fluid and aerodynamics laboratory, spanning basic and applied research for multi-phase fluid flows and aerohydrodynamics. His experiences cover a wide range of applications that includes aircraft, wind turbines, marine vehicles, atmospheric flows, chemical reactors, nuclear waste processing, food processing, biomedical, and acoustics. And thank you, Michael, again, and please, time is yours.
All right, well, thank you, and thanks everyone for having me here. I think I'm pretty happy to be here and present some of the work we're doing here on the Dragonfly program. So I'll give you an introduction to what it is. I do want to say that you have to get a lot of credit here. A lot of the student team that we have is doing essentially above and beyond a typical grad student. They're developing theses and research and papers at the same time as working on a mission critical kind of like engineering type work. So it's pretty exciting. I think for them, they get to do something that I think a lot of grad students don't get to experience. So here's kind of a list of just some of the grad students working on this, and we have a couple. I'm not sure how familiar you are with the Dragonfly project. It's a project that's been awarded to Johns Hopkins APL, same group that sent out, I think it's the New Horizons mission to Pluto just a few years ago. So we're working with that same group. Lockheed Martin's doing some of the aeroshell stuff. Penn State is kind of a rotorcraft expertise, and then NASA. We're primarily working with the EDL branch. So I just want to give you, before we get started, I want to give you a brief introduction of myself. That's me. I have about maybe 10 PhDs, 9 master's students in our group, maybe about 15 undergrads. We do work in basically CFD is our primary function. So computational fluid dynamics, and we'll talk a little bit more about this, but what it is a high fidelity model for basic fluid flows and aerodynamics. In the context of that, I do aerodynamics, multi-phase flows, and it's kind of like complex modeling. A few projects that we've been working on is fluid structure interaction. Here you can see the flows moving from left to right, moving behind a fluff body, creating a lot of turbulence back here, and exciting, almost like kind of like a flag-like motion. This is actually a viscoelastic material. And Here's some other work looking at controlled UAVs. This is actually using CFD as a simulation environment to replicate controllers virtually in a high fidelity setting prior to doing testing. This is work that Wayne had been developing. Also looking at aircraft, here's some sample calculations of essentially F-35 and impingement type cases. So if you're not familiar with F-35, it has a hot jet and a cold jet, and it leads to a complicated ground interaction. And I've also been exploring sandblast nozzles as well, specifically looking at how do you quiet them. So it's a solid laden high speed flow. Yeah. May have went overkill on the videos.
We just,
Is it snow?
It's thinking. Yeah, I gotta restart. Bear with me 1 second.
Is that a Mac?
It is not a Mac.
Good.
It didn't give me any problems until I.
yeah, it was, we were. Very fun, there was no problem.
Or when you were not doing Zoom,
We
it was
tested.
working?
Huh?
When it was not on Zoom, it was working?
No, we were on Zoom, it was right before the talk started.
All right.
Okay.
Then there's atmospheric flows. Here's a sample atmospheric flow that we were exploring, specifically tornadoes. So this is a tornado. We have like this huge model tornado that we could move around. These are buildings. We were trying to replicate an actual tornado event in Pennsylvania a couple years ago. Other things we've been looking at is looking at details of rough features that relate to kind of like roughly manufactured aerodynamic devices. So you think of now people are doing 3D printing of everything. What happens if you 3D print a rough surface? What is the aerodynamic impact there? So we also had looked at that in the context of ice. And then here's another case. This is actually a nuclear waste vessel, so filled with nuclear, basically solids. So it's a 3D flow that is kind of actually relevant to the Hanford waste treatment plant. Have you ever heard of that? The big disaster. But this is one of the waste treatment facilities. Here you can see kind of like this. These jets that pump an impinging jet and picks up a whole bunch of solids to mix within the vessel.
Which plant?
It's called the Hanford Waste Treatment Plant.
When was that?
It's still going. It's been going on since
Oh,
1970, and this was about 10 years ago I did this.
All right, sorry, thank you.
They've gotten nowhere on it. So this is some of the work that actually GD's funding. This is a spacecraft interacting with rarefied jets, interacting with space stations, trying to understand kind of the life of space stations in the context of operations and station keeping. So it's a complicated problem in that it's CFD, but it's not continuum. You're familiar with CFD, it's mostly continuum assumptions. This is in the context of a hybrid verified and continuum regime where you have a continuum coming out of the jet and they expand and basically leads to surface pressures or deposits on the space stations that can eventually degrade the life of the space station. Also doing work with Dr. Kothup. I think she did a seminar here maybe last year. We're looking at interstitial flows within bones. The Jackson's doing this. And we actually had a Blue Origin flight to actually test some of these features. It was on the wonderful failed Blue Origin flight, so we're still waiting to get back on there.
Was that the one with Space Tango?
Yes, it was with Space Tango. Yep.
So that's the reason why you don't have space data yet, because Blue failed the flight?
Yes.
Okay.
I mean, we can always use more time, so maybe it's not. We redesigned. So this is actually one of our preliminary designs. You can see the little pores that we actually got from 3D scans of mice. We had this microfluidic chip that we were going to test in microgravity, try to understand how nutrients sediment in microgravity in these very small scale flows.
Thanks.
And here was some other work that we did a couple of years ago, looking at impinging high-speed jets, you know, in Mars. We didn't quite get the soils working there. It's a pretty tough problem, but we were able to get some preliminary data to understand where it's going to kick up dusts and so forth. Okay, now let's talk about Dragonfly. So that's really why we're here. So Dragonfly, I have a nice video here. It does a much better job than I could describe, and it does it in just a minute. No music. Well, I get the music, you guys have it.
Who made that video? Do you know who made them?
What's that?
Do you know who made that video?
Oh, NASA did. I don't know who in NASA did.
Yeah. There's like oil on the surface.
It's like, I don't know if there's oil, I know there's methane.
They said hydrocarbons.
Hydrocarbon.
Oh, okay. So there's the Dragonfly lander. This is kind of what we're focusing on. The drill.
There was a night proposal to send a submarine. to One of the nations.
I was gonna mention
Oh,
that too.
sorry.
I actually did some I used to work at a marine laboratory at Penn State. One of the people works pretty closely with the group at Johns Hopkins, and I was kind of in a little bit of a discussion there. I think the lakes are actually supposed to be effervescent. So, or the oceans, so they're kind of like foamy, like beer or soda. And it was kind of like a concern, because I did a lot of cavitation work in the past. If you had a propeller in these effervescent seas, how's it going to behave? Is kind of the discussion. But it's actually a cool idea. If you aren't familiar with it, this is kind of a follow-up to the Cassini mission, which explores, its main goal was to explore Saturn. But they had this Huygens probe. And now I think one of the main developers of the Huygens probe, Ralph Lorenz, is kind of the mission architect for Dragonfly. There's actually a image. So what it was is a little probe that went straight through the atmosphere and landed in dust, or in maybe one of the sand dunes, I forget which. But here's a kind of an image that it took of the Titan surface. So we can see it's very kind of dirty, dusty. But they have a lot of different features to Titan's kind of landscape. They have sand dunes, they have lakes, they have all kinds of stuff. Okay. So why flight? So just trying to give you a very quick overview of why they consider flight. You know, in general, I don't know if all you all know aerodynamics well, but the concept of aerodynamics is you have lift equals weight, right? Weight is going to be proportional to density. Okay, so by that, your weight is going to be proportional to your lift, which is density times velocity squared times some aerodynamic coefficient. So Titan basically changes this and weight via gravity. So when we look at this, these two parameters, the density of Titan is about 4.5 times that of Earth. So you can see that in this side of the equation gets beefed up.
The atmosphere? Or the density of the atmosphere?
Yes, sorry, yeah, the atmosphere. And then the gravity on Titan is about 1/7, so the weight component goes down. So it's relatively easy to fly there. We kind of just look at it from a general perspective. We can look at just a basic terminal velocity equation for large objects. So the large object drag coefficient, so a large round object, the drag coefficient is always about 1. No, about 0.4. So we know what this is. So what we could do is just develop just some scaling relationships to understand the ratio of how fast something settles on Titan with respect to Earth. Put in all these numbers and you can see it settles about 20% the speed and then it does on Earth. So when you look at how things settle on Earth, Titan, and Mars, that's kind of like the visual aspect of how things. So you think about Mars, we had recently, so NASA recently put the Mars Ingenuity up. That's a tough environment to fly in, but it wasn't a main lander. Keep in mind, it was kind of like an isolated vehicle that flew around the main lander. Dragonfly, the main difference is it's the lander. It has all the powering unit, all of the scientific instrumentation, everything. So it's a big step beyond Ingenuity, and it is in a atmosphere that makes sense, or a scenario environment that makes sense. So and for that reason, I think Titan makes a perfect first exploration mission to explore a flying vehicle in these different planets or whatever, or moons. Okay, so the main kind of quantity we didn't talk about is here, this aerodynamic coefficient. It's a lift coefficient. We have all kinds of aerodynamic coefficients that correspond to how we understand flight, right? You have drag coefficients, lift coefficients, pitching moment coefficients. That's the big gap. We know pretty much what the density is. We know gravity and weight, but we have no clue what CL and other aerodynamic coefficients are going to be. And one thing you could do is test this on Earth facilities, kind of like the obvious thing to do. But the problem is we cannot get to the right scaling. The atmosphere is very dense. The viscosity is actually pretty low. And because of that, we end up with scaling parameters that are not well suited to Earth facilities. So does everybody know what a Reynolds number is? I think most people said yes. This is the main aerodynamic scaling parameter. You don't match this, you aren't going to get what you aren't going to match the aerodynamics. And it's very difficult, even in the highest Reynolds number facility that we have. So that's the TDT, or transonic dynamic. And the reason being is we could increase the density in this facility, we could change the viscosity, but we can't get the length to actually fit in this tunnel, which is a very large tunnel, by the way. And you can see how big it is with these people down here. We can't actually match this scaling there. So this is some Dragonfly testing that was done in the TDT. It's just the rotors at full scale dimensionally, but it's still on the order of half scale in terms of a Reynolds number. And it's in a kind of a complicated region where I still don't even trust that at half scale. So because of that, and regardless of the scale, whatever we could do, we can always scale it back to our lift coefficient, which we can use different fluids, different speeds, but we have to match this Reynolds number, and we aren't able to very well in these facilities. So we have an underlying challenge of really understanding the aerodynamics of Titan and demands model. You know, another kind of challenge with respect to these Earth scale testing is this facility specifically is booked for years out. And we'll talk about this in a little bit, but we have a very tight timeline. We have a launch date of 2027. If we have to wait for every updated iteration for the TDT to happen, we're never going to do anything. We don't have that much access to this facility. There's a lot of competition at NASA with other folks. So this is kind of the landscape we are in. Now let's talk a little bit about kind of the flight scenarios that we expect to see on Titan, the Dragonfly. So we have a launch date somewhere around June 2027. I think it's slipped. It used to be 2026. I think we're at the end of the window. Here we are at Earth, supposed to launch, go into orbit, then reach out here in around 2034. So it's a long mission. I remember talking to some of the PIs about this. They're like, I'm ending my career in this. Okay, so 2034, that's a long time. And once you get to there, what do you do? This leads to this EDL, or entry, descent, and landing. What it does is demands safe arrival. It's one of the critical parts. You know, I think I think it's one of the most concerning parts of, the operation of actually getting there, because we've had failed events in the past. So what happens is they go in this aero shell. So the front side of this, I don't know, well, you can see it is a heat shield. The back side is just basically holding it in. And it lands, it takes about 10 minutes, and then they deploy these drogues and parachutes. And thereafter, the lander actually exits. So in the context of where we are, NASA's EDL group's doing most of this. UCF's group is doing a lot of this part, and then the Penn State group is doing this part. So this part is kind of like reentry. This is referred to as stowed and posed. That's how it actually exits. Yes.
So, it's landing and then sort of deploying everything and flying away, or it's dropping it and starts flying as it's going down?
So what's going to happen is it's going to be supported by a parachute. It drops this heat shield and it kind of comes out in flight.
And then it starts flying on its own?
Yeah.
Ooh.
So it's kind of similar to how, well, not Ingenuity, but the most recent Mars mission was, where it comes out and it gets lowered down, or it starts flying as soon as it comes down from the.
It starts flying as soon as it's in a parachute.
Okay,
So it's complicated. It has a lot of complicated underlying aerodynamics there that we really have to understand. That's one of our jobs, is understanding everything in this region. Penn State's job is how do we get from the shell, how do we start flying from there? There's a few complicated flight scenarios there. I'm not going to discuss them, because it takes a long time to discuss each one. So the one that you just kind of described, it's called Preparation to Powered Flight, or PPF. And this is the NASA video showing the nice, pretty picture of what it looks like. You can see it being supported by a parachute, kind of just wobbling around, and then kind of pops out and just flies.
So it's dropping, and as it's dropping, it starts propelling?
Yep. So there's kind of like two critical phases here. One, stabilizing this back shell that's supported by the parachute. That's our job. Penn State's is called Transition to Powered Flight. They have to deal with something called vortex ring state. So when you start dropping a helicopter, you descend too fast, the propellers start going into their wake, and that leads to some complications with flight.
So is there a lot of Earth experience with doing that kind of operation, like dropping and start propelling as it's dropping?
There's no. Yes.
So the folks at Penn State actually did some of that, like on Earth. But I think, as you'll see later on, it's a little bit of a different scenario in the context of Titan, because we have a lot denser atmosphere that we have to worry about.
Something easier to do there, is what you're saying.
Well, I don't know about that.
It's
It's
just
counterintuitive.
such an exotic thing to do, and I'm surprised that, they would just try it out on a moon of Titan. For the
Oh, there.
first thing.
It's not that they're trying it out. We've been beaten up all
Yeah, I see.
ever since last June about this.
Yeah, okay.
Like I think the NASA people, they have people from NASA, EDL, NASA's rotorcraft groups, NASA's, or Sikorsky's rotorcraft group. And we have a whole team of people.
Yeah. An exotic thing to do.
It is. And Ralph, right?
Yeah.
He was in a meeting once saying, I would be disappointed if they seemed to fly out of this.
I mean, certainly the better way to land, right? Because you can get yourself landing.
Yep.
Yeah.
Exactly.
So, yeah, okay. Thank you.
So that's what they picture it, and then this is kind of what they put us to. They make it sound like, they give us extreme events where the back shell's supported by the parachute, and it's wobbling all over the place. So that's not a very favorable scenario to just start releasing a lander, right? If everything was nice and stationary like this video, it might make more sense. Here's what they're kind of planning on doing, and these are, again, some of the extreme events of oscillations that they're putting us through. This is kind of this closed mechanism that pushes it out. It can't start the rotors until it's pushed out because they're kind of limited in the aero back shell. And then it flies out like this. So they do not want it to actually go into free flight while it's wobbling like this. And again, it's an extreme condition that they're kind of saying, you better be able to control this, slow down these or dampen these oscillations, otherwise you aren't going to pass your design.
So it's like, it's being descended a little bit, and I see the rotors are like turning a little, so that's supposed to slow down the oscillations?
Well, that's the whole plan, is to use these rotors to actually start controlling the dynamics of this system so that
While
you can.
still attached.
Yes, yes. So that's the goal. Control the
that's-
parachute dynamics using like.
Is that attached to the parachute still?
Yes, this is the
Okay.
back of the parachute.
So,
And I'm gonna go through a couple slides beyond this where we're not gonna see the parachute. Assume it's there. We aren't modeling the parachute, just assume it's there. But the parachute does exist. So this is kind of the general process. We start off with a full aeroshell. Then we are providing the Lockheed folks kind of like information on the heat shield and the heat shield aerodynamics. It's a little different from Mars, as we can see. Things fall a lot slower on Titan. If you're already descending and your heat shield doesn't fall off, it'll cause a complication. After the heat shield descends, we're in this what's called a stowed configuration. The stowed configuration is basically the lander is stuck in this back shell. The rotors are not able to move. They're kind of limited in the back shell, kind of like in a direction like this. So that you cannot, so it could actually fit in there. And then they go into this post configuration, like on the previous video. And there we have rotors that could help kind of, we could start turning on the rotors to help control this. So how does the control work? Here we have a picture of basically a Dragonfly lander, some of the 8 rotors. It's not clear. This is a coaxial rotor. We have 4 coaxial rotors in Dragonfly. So by coaxial, you have 2 rotors on each arm. They're rotating in opposite directions. And one of the, and there's one other special thing that you probably haven't noticed yet, is that they have this cant, or it's angled upward. And that angle is supposed to provide the rotor thrust slightly inward. And the whole idea here is you get a Z component that basically is intended to reproduce or to give you lift or thrust to counter gravity. And then you have this Y component in this coordinate system. And what that does is it provides a moment. So it gives us a moment to de-spin. And that's one of the modes that they're expecting to see in this parachute. So the whole idea here is to use this, and use various configurations of the rotors to prevent that oscillation from happening. And that's what we're referring to as de-spin. So you can kind of see this picture here, showing how we're using the rotors to kind of control what's going on. Okay, so yeah.
Is there like a lot of wind on Titan?
I believe there is, but I don't believe it's that strong. I think it's like 1 to 2 meters per second is what
Okay.
they expect.
Okay.
I mean, they have one data point.
Oh, so wind speeds is not something that is able to be seen by either the scene or beacons at the time?
I think they were. I will say that I haven't been too much involved in the wind speed. I think it's kind of like aerodynamic noise for us.
Okay.
The Penn State group had done a little bit of work modeling the atmospheric boundary layers there and trying to understand it. And I think the general consensus was it wasn't a major issue.
Okay.
Obviously it isn't, it can be windy. They have sand dunes. So it's possible it's somewhat strong, but. So this is where we have our computational fluid dynamics, or CFD. What it is basically a model that solves varying equations, conservation of mass and momentum. We use some kind of trickery using what's called the body force to provide kind of estimations of what the rotor blades do. We solve these equations on this discretized domain that represents the lander boundary conditions with certain flow conditions and these sorts of. In the context of this, we're doing all the compressible modeling. Titan is, unlike Mars, our lander has to deal with very incompressible flows. It's actually very favorable with this. And we're using turbulence modeling. That is a result of high Reynolds number type conditions that we have to deal with. Here's just a basic simulation of this PPF configuration. And you can see that the model is able to directly resolve all the intricate details of the lander, what's inside the back shell, no separation around it, and it's all colored by pressure. And pressure is a key component to providing aerodynamic forces. So here's a couple of simulations showing, they're dynamic simulations showing the D-spin. So what we have here, and I'm not going to say this exactly, Wayne, if you want to correct me, please do. But we have these rotors. You can see we're activating them with the body forces on here and here. And you can see that they're varied in time by RPM. So when the rotors are activated here and here, we have thrust coming out. And what we expect is this one having an inward component, this one having a component this way. We're expecting a rotation in counterclockwise configuration. One of the things we started noticing with our modeling is, you can see it here. This is colored by pressure. Blue is low, red is high. And what we're noticing is that the rotors are pulling an accelerating flow along the side of the body. And they give us a basically reverse torque of what we're expecting. So what we've kind of identified was that the expected method that they planned to control this was actually behaving exactly opposite of what they wanted it to be. So it was kind of funny, led to a lot of work. It's still leading to a lot of work, but we did a ton of studies to really understand this D-spin thing. It was a big thing actually Corey had done all last summer. Yes.
So do they are you only activating 2 of the rotors in the beginning and then 4 later, or?
Okay, so this is when the aeroshell's attached to the lander. So they're physically attached. We didn't add that into the model, but they're physically attached.
Okay.
And imagine the parachute up here. And it's wobbling around, going into some sort of spin. What we're trying to do is use.
So you use the two rotors to cancel out the the oscillation, and
Yeah.
then once it drops, the other 2 activate.
Yes, it's
Okay.
actually other 6.
Other 6, yeah,
But yes, that's correct.
got it, okay.
In this simulation, all of them actually turn on. So like the other curves at the bottom, you can see,
Mhm.
those ramp up, all of
Yeah.
them ramp up to 100. And then the bottom rotors on the other sides ramping up to either 600 or.
Okay, okay,
So yeah, that's a good point. The other 6 are at 100 because if they're just kind of floating in the wind, you might end up windmilling, you end up with the rotors going the wrong direction and you can't get things working properly.
gotcha, okay.
So we were able to identify, so 1, it added a lot of work for us, and it added a lot of complications. But 2, it's kind of exciting that we actually we feel like we found something that when they start testing experimentally, they'll see very similar things. And it could have, we think we could have alleviated an issue that they may have not found downstream. So it's kind of cool, I think. Just trying to think of anything else. So after we were beat up for about 3 to 4 months. We're still getting a little bit beat up, but I think people are finally starting to believe what we're saying. And I say that in you know, it's kind of like a unexpected phenomena. It's really hard to take these unexpected phenomena beyond like what we're seeing in a computational model. Computational models don't always give you the right answer. And because of that, we did tons of validation. All the validation cases we could think of, we're missing the real data, and it's leading to a whole series of tests, including drop tests from parachutes on similar type behaviors. The problem is they're doing it all on Earth, and there's and on Earth, the propellers have to work harder, and it takes away the underlying aerodynamics of the body. It's the ratios aren't right. When you're working with just propellers, the propellers are just, or in air, the propellers are just dominating everything. And we still expect to see this interaction in on Earth, but not to this, not to the degree that we see on Titan that we're observing. Water has this, actually this kind of phenomena happens all the time, and it's definitely more prevalent in water. So for example, torpedo has a propeller, it has a shroud all the way around it. That shroud is one, it has a lot of aerodynamic loads or hydrodynamic loads on it. And we're seeing the exact same thing. It's just when we talk to the helicopter people, they don't see it in helicopters because they don't have shrouded motors very often. In any case, after a whole bunch of studies, a whole bunch of shaping redesigns, we were able to get to a point where we were able to alleviate this issue. So here's our Z moment as a function of RPM. And what you can see is at some point, you get, a very consistent behavior. So right here, basically the body torque's canceling the rotor torque, but you exceed some threshold and it starts to work and function as expected. But that was not the case in our original geometry, so we had to do a lot of work to kind of get around that. Okay. So again, this issue kind of remains in contention. People are kind of coming around, but it's really a main issue that we have to handle for critical design review, which is coming up this summer. Okay, so a few other things that we've been working on. One, the outer mold line. We're really, this is kind of in our boat. This is kind of one of the things that we're really driving. I'll just give you a quick review of kind of how the evolution of it. This is kind of the 2017 version of Dragonfly. It's very crude, very ugly. Then we moved into this 2018. So this is the one that actually won this Phase B New Frontiers kind of project with. And now this is kind of where we're at. And this is, and some of the differences that kind of came around is we had a lot of different things going on. One, they increased the aeroshell size on us. We actually, I think, doubled the aeroshell size. They didn't increase the budget, but they doubled the size. And it just meant we get to grow the thing, and then everybody adds a whole bunch of stuff, and it just is a snowballing effect to weight and structural loads and all kinds of stuff. So we're still dealing with thermal issues. We're still dealing with structural issues and some slight changes. And here's something for the planetary scientists. We also have to deal with aerodynamic junk, which is all the cool stuff that you want to put on there. Yes, they are pretty for us. So I actually had it labeled as junk once on one of my plots. And Ralph actually saw it and he just laughed. Okay, so once we get these outer mold lines, what we're doing, and we get some of the mass properties and all kinds of stuff, we do full characterization of the lander and forward flight as well. This is a lot of the work that Wayne's doing, and what it involves is tons of calculation, on the order of thousands of calculations. And we're not just putting it in different orientations, we're trying to trim it as well. So a trim state basically means the moment and weight, or the moments and forces are balanced. So we're trying to understand the different the aerodynamics in any configuration that the lander can fly in. So this is kind of a typical thing to do for most aerodynamic bodies. And you gotta do it just to be sure that you have the correct the correct understanding of all the controls, all the flight performance and other things. So here's just a subset of all the cases that we ran. Each one of those points corresponds to a point that Wayne actually ran. He had a whole bunch more. He's developing methodologies to kind of streamline this process and better process the data as well. The other thing we've been looking at is once they've actually took our data, they started putting it in their flight simulators and found that there were flight instabilities, specifically a yaw instability. So the yaw would be if if this goes into oscillation in this mode, right? And the flight instability is basically one of the things you want to avoid at all costs for an aircraft. You can think of an aircraft, they have that rudder in the back, that's for yaw instability. And we don't have a rudder here, so we were kind of in a problematic state. So after evaluating hundreds of configurations, we've actually got to a state where we have yaw moments that are in line with something that we can control. So it's and some of the problems that we had here is all the different requirements we had. We had to fit these rudders. Yeah.
So when you're saying configurations, when you're changing the shape of the body?
Yes.
Is that what you're doing? Okay.
Yes. And I'll show you what it looks like in the next slide. It was really challenging though, because it has to fit in the aeroshell. It can't run into rocks and get stuck on rocks. It can't interfere with the rotors. They have this MMRTG, so this big can in the back, it's a powering unit. Apparently that's like the biggest issue is how do you put that in at the end, right before the launch? And if anything's in the way, it's basically causes a nuclear concern kind of a thing. So it's right there. And it made it really hard to do this. But eventually we got to a cured state. So this is kind of what the fins ended up looking like right here. And some of the fairings that we're putting, are you not able to see it? You see it better now. These are our fins. They're not ideal. They have a lot of interference with the MMRTG, but we would move them just a little bit with respect to the MMRTG and they would become ineffective. So it's really kind of complicated. Right here, I don't know if you see it, but we had to meet some angle because we didn't want to get stuck on rocks and so forth. That's some of the other things.
You added all these red cards?
Yep, those are releases. So
In the weight wise, they didn't constrain you there?
not on that. We had it was a big concern, so we actually had no weight requirement. Like they would do this no matter what.
And this will be metal?
I think they're planning on putting some sort of carbon fiber around the periphery and putting some sort of like, I don't know what they want to put on the side. Do you remember, Luis?
On the side of the fence,
Yeah,
I think it was something carbon fiber. Everything else is a type of foam.
yeah.
Oh,
So a lot of this is foam. They're kind of co-using it as insulation. We're trying to double use it as a fairing to prevent, to lower drag and extend range. It's kind of a fun battle.
yeah.
And sometimes we lose. We weren't going to lose on this one because it's a no-go for flight without that. But with these ugly things here on the shoulder, thermal people won. Okay. All right. So here's a couple of other things. We've also been studying the fluid dynamics during landing. Here you can see the lander as it's coming to the ground. This white thing indicates the ground. We can see here is velocity to the center line. Specifically, it's I think blue is an upward velocity. And as it lands, basically what we'll see in the next few slides is it kicks. You're basically having these rotor downwashes kicking fluid up and it hits the belly of the vehicle. So you kind of see that here. There you go. This is at the side of the vehicle. You can see that it reduces. But once you land, it gets kind of complicated. And then here's right to the rotor. So the rotor indicates downwash. And what it is it's coming down at the rotor and coming back up at the belly. So here's a kind of a view of what it looks like in 3D. So this is different elevations. These are kind of like streamlines seated at high shear regions. We're kind of looking at that because of dust. But you can see how it starts to get kicked up. Right here, you can probably see it the best. Here, the underneath the rotor is very clean. It kicks it up right into the belly. So that leads to aerodynamic effects. Here you can see the upwash into the belly. This is lift as a function of elevation. You can see as you get closer and closer to the ground, the lift actually changes by about 300 meters here. So it's actually helping. So that's actually a good feature because it's kind of like a cushion as you land. If you look at the drag as we come in the ground effect, it's almost not effective. So it's not going to be moving in the axial direction very much. We look at pitching moment. This does have a slight effect, and it has a tendency to move the nose down just a little bit. And then when we look at rotor efficiency, so this is thrust as a function of elevation. Let's just focus on these ones. What you can see is a general trend when you start losing a little bit of thrust as you get closer and closer, but not as bad as what you gain in lift. So it gives us a lot more confidence in terms of landing and not seeing very complicated aerodynamic phenomena during landing. Okay, so the next thing we started studying was wall shear, and as it relates to kind of like kicking up dust. So I don't know if you all know, one of the main aerodynamic or fluid dynamic parameters to kick up dust is wall shear, something called Shield's parameter. And the higher the wall shear, the higher the shear stress on the wall, it's going to kick up bigger and bigger pieces of dirt and dust. So you can see as it lands, you can see this region here in green is going to indicate a bigger and bigger region of where it's going to start kicking stuff up. If we look at the velocity magnitude just off the body, you can see a lot of some of the underlying features. One thing you might notice is this region here, basically having a funnel effect. And it basically leads like a fan that goes vertically over here. And it has another one that goes, there's 4 of them. So it's kind of like a big upward jet in the belly of the vehicle. If we look at some assessments of fine particulate, so these are 50 micron. What you can see is as it lands, this is at 5 meters, it just kicks stuff straight laterally. At some point, it starts kicking stuff up into its belly. It gets pretty, I think probably the worst case scenario was about 1 meter. And then in this case, it's pretty bad. You can see there's dust kind of everywhere. So there's a rotorcraft phenomenon. It's called brownout. This is kind of what we're trying to understand. And it leads to erosion. One of the main concerns is eroding some of the windows on some of the visualization, like the LiDAR. And also that gives you a visual barrier. It can also lead to erosion of other features on the rotor. So one concern is getting erosion on rotor blades, leading to basically vibrations. If you have too much damage on one rotor blade, it can lead to some sort of vibration, which would be a major issue. But we're seeing a couple of different things. We have an impingement fountain, so an upward jet at the belly, and a fan-like outwash at the kind of like the lateral sides. It's actually very similar to the joints that F-35 that I showed you before. They see the exact same phenomena. All right. So another thing we're doing, I'll try to breeze through this a little bit quicker, but we're also looking into flight sensors, trying to understand, using these tools to understand how to do all the sensing that they need to do. So one thing that we're doing is pressure sensors to detect speed. And Wayne's doing this for this entire database so that they can take pressure sensor data and infer what speed they are for a wide range of flight conditions. We also looked at condensation. There was concerns about, you probably can't see this that well, it's too small. But what it has is a rotor blade with these tip orifices that are condensating in the wake. So you can see kind of like a cloud of little droplets right from the tip vortex. You can sometimes see this on an airplane when it takes off. The tip vortex will leave a little white cloud. That's due to lowering the pressure and leading to condensation. Well, there was some concern there that maybe this rotor, this wake would, these kinds of things would persist below the LiDAR and distort visualization. So what we did was looked at a few different key conditions at different altitudes to understand the effect. And looked at some flight conditions using some of our advanced modeling and found that, really these areas where we expect to see condensation was actually limited to the space one, which was basically a very high altitude. And it was mostly apparent on the blade itself, on the outward tip, not so much in the tip vortex. So it gave us a lot of confidence that, condensation isn't going to deter some of the LiDAR. And here's kind of like an outline of some of the detail that we had. If you're interested, there's a paper here you can look into. We also looked at some of the meteorological sensors, and this is called dragnet. What we looked, I think it's going to be here parked, and they have these sensors all over the aircraft that are kind of like little wind vanes. So here's one out here by the rotor. We're looking at different sensor locations, and we're putting this lander into different wind orientations and different flight speeds to develop kind of like a correlation so that, for example, if the wind's coming this way and we have our sensor this way, we want to be able to correlate what was the wind speed when it was coming from that direction using the sensor right here. It's in the wake. Also, at some point we did some thermal analysis to help support them. They had no clue what the convection coefficients were going to be in free flight. So we helped provide some of that data. I'm a little surprised, but they didn't come back for more information. I thought it was pretty useful. And we're still kind of battling the whole thing. So just the last thing, I do want to highlight Ralph's books. He has like 4 books on this stuff, probably even more. I think he writes like a book every 6 months. But we actually got some pictures from our results in this book, I think, or maybe it's this one. But they're pretty good books. Actually, one of my students that worked on this for a day got a signature saying "good work on Dragonfly," and all the people really doing the work were either at home attending a meeting or at APL attending a meeting. All right. So conclusions. So as a team, I think we're doing a pretty good job providing what has been referred to as mission critical data for Dragonfly. So it's been pretty exciting. A lot of work though. Our primary efforts are basically characterizing the aerodynamics, really for a wide range of the flight range or the flight conditions. So there's PPF, or preparation for powered flight, and forward flight. So when I say aerodynamics, I primarily mean the fuselage aerodynamics. So Penn State's folks are doing the rotor aerodynamics. When you come to the title, you wonder, like, why can't you do this on Earth? We're proposing CFD as a very good tool to help understand what's going to happen on Titan physically here on Earth. So that's kind of where that came from. And I want to emphasize that it's really shown to be a multifunctional tool that really helped understand a lot of the key questions that they had. And I think they find a lot of value in it. And it's ranged from aerodynamics, thermal analysis. Here, I say structural loading. I think maybe I didn't mention, but Wayne, when he's generating his thousands of cases, he's going to provide loads so that that ensures them that the fins aren't going to break off, or the other various components aren't going to vibrate. And we're also starting to look at debris interactions. Well, we have a lot to come in the next year, specifically refined design. We have a critical design review this summer, so a lot of work coming up. We're also, always trying to make sure our models are accurate. It's a huge leap of faith to go off a computational model. And that's what we have to continue to do. When I say that we're evaluating model accuracy, some of our team is kind of looking at refined models. The NASA rotorcraft people are looking at refined models. And we're trying to compare between what they have and what we have. We're also working with the NASA experimentalists and making sure what we have is represented well, or can represent their experiments well. So there's a lot going on there. And that really leads to kind of like the verification and uncertainty quantification. So I don't know if you all know about uncertainty quantification. It's something that just made my eyes glaze over when I was a student, but it's really important. And it basically is a really important tool, one, to understand the limits of your analysis, and two, to understand and make choices for your analysis. And then the last thing is ground interactions. And I keep on talking with Joe about doing the ground interaction. We want to do one other thing with ground interaction, and that's actually using the rotors as a measurement device. So they want to actually fly this on one of the sand dunes and just kind of turn on one set of rotors and use the tip vortex to kick up dust. And if they could use that and they want to use that to identify specifically what's the dune mobility of Titan. And it's kind of weird because I think it ends up like closing out their entire atmospheric model of Titan. So because they have this like big dunes, and if they could just, you could tweak all kinds of things, but that's the one parameter that there's a lot of uncertainty about. And if they could kind of refine it using this, it would help kind of close out that part of the mission. But that's a small part. I mean, I think ultimately they want to look for kind of like primitive forms of life and so forth. Well, that's all I have. I guess, are there any questions?
Oh, okay. Okay, let's thank our speaker. Hi, Michael. I think I have a question.
Okay.
So what is the main benefit of using stacked rotors instead of two side by side? I thought we'll lose the efficiency by stacking up.
Oh, yeah, that's very important actually. So the stacking is, so if you put this as a quadcopter without the coaxial rotors, and you have one rotor fail, you're all of a sudden, rotorcraft, it wouldn't work like a three-legged table. It would be like a four-legged table with one leg out and it would just fall over. It'd be very hard to control it if one rotor failed. So really it's just redundancy. So this thing, if it has one rotor fail, it's actually designed to continue to fly. It could have a second rotor or a third or a fourth rotor fail, so long as it's not on the same coaxial. Does that make sense?
Yeah, thank you.
How big is the actual like Titan, the lander? The actual rotorcraft, like how?
I'm gonna, okay, Luis probably knows this more, but I'm gonna guess 4.5 meters, the size of the inside of the aero shell, the back shell.
Okay.
That's like the limit to everything. We kind of explored options to make it a little bit bigger, like have some mechanical fins that come out. But, we're at the same time, you've all heard the mnemonic, keep it simple, stupid.
Yeah.
It's very important in space because nobody can touch it once it's launched.
Kind of educating.
You had a number of students working on this project, all grad students, or we have some undergrads.
We have some undergrads too, yeah.
But the grad students, are these a part of the thesis or dissertation, or is it just a project we're working on?
So Corey has his whole thesis working on the kind of like understanding the preparation for powered flight aerodynamics. Wayne has his thesis oriented about all kinds of different things, kind of oriented around it. We've been exploring machine learning of these interactions. kind of like, he also started exploring Mars flight, or engineering flight, and all kinds of other stuff. Luis did his thesis on fairing design in wakes. At that point, we kind of didn't know what we were able to publish or not, so he kind of just separated from it. But that's what his thesis is on, and then Jackson's going to continue doing what Corey's been doing. So he's going to do.
Can they all publish papers, or is this data still?
Yes,
They
they
can
can all
do
publish it. Yeah. But it was kind of we were unsure at first,
Yeah.
and then we found out that it was only the Johns Hopkins people and NASA people that need all the go through all the hoops. And then, yeah, Edward's doing the heat shield stuff.
And that's great. It's rare to see so many students under one PI working on one mission. For all these different subs, that's great. I like this. And I don't know how many of you, with your experience, if you try to get an internship at a NASA center, especially in Langley or Armstrong, you guys have a very good chance of getting an internship.
Jackson's going this year. Luis was actually interviewing with Langley. He's graduated now, but I think Raytheon's paying him more, so.
Yeah, I know, I've heard that number of students are leaving NASA internships because they're getting paid more.
Yeah.
So they are going to increase the stipend next year, I think. So, yeah.
Okay. But yeah, I think Jackson's going for his second year, so. Great. And just another comment too. Dragonfly puts out I think a call for proposals for PhDs to fund them on just general science missions. I don't know if you've seen that at all. But every year they fund maybe about 2 or 3 PhD students. It might be I think at first they wanted not to do UCF because they were already funding UCF, but I think that's kind of went away now at this point. Oh yeah.
How long are they hoping that Dragonfly will be able to fly around Titan?
I think they only need to do like 20 flights, something like that. And it's kind of funny because we talked with like the Sikorsky people. You know, they basically like nail us. Oh, this thing's gonna vibrate like crazy and fail. Because for Army, which is what they normally build them for, they fly hundreds of flights. so or maybe not hundreds, sorry, thousands of flights, and vibrations is a different beast. We kind of are in a different scenario where we could kind of accept some of those vibrations, so long as they aren't, you remember these SN curves, right? The higher the vibration, the fewer the number of things you could have that happen. We could be on the lower side. They have to be way on the extreme side.
So it's mapping only one part of the moon, like one region of the whole moon. Like the 20 flights, how are they distributed?
They are distributed. I think they're they aren't going by the lakes. I forget where they're distributed. I know they're supposed to hit the dunes. And I know they're supposed to hit certain regions. I just am not sure where they are. If you remember, they have a drill there. They're basically planning on drilling into the soils, pulling it up. Some of the other junk is like, they have a pump that's sucking it up, and they have a.
That's a crazy one.
They have a seismometer too, so they're trying to measure.
Yeah. Side of the
It's like
regolith.
mid-latitude in equatorial regions,
Might
like a specific area. I don't think they will go around.
Okay.
I think if you're interested too, Ralph did a presentation to AIAA about 2 years ago.
Mhm.
I could send it along. He talks about everything. He's really the expert on that.
Sure.
So if the D-spin that you tested is not going to work, are they thought it would. Are they using a different method to stabilize it? Like if it was the vibration, is there a way that they can use like high frequency vibrations to stabilize it or something?
I don't think high frequency vibrations, I think what they're aiming at is kind of like jets. And I think what he was mentioning before, like the sky crane we talked about, like, we kind of concluded that that wasn't gonna work. I don't know if you remember anything else, Corey. There was like we basically did, Corey mostly did like,
Well, one thing was you can cancel out your rotor torque with your thrust, so if you can use the rotors at canted hours, you can eliminate
oh yeah,
rotor control that they technically wanted to do, but because we don't have actual in-person experimental testing it, and they don't necessarily fully trust the suction force existing from CFD as long as it's not like compared yet to actual testing, it would be possible if that existed to use that suction force for the control and just basically get rid of the rotor torque generated by the rotors. That's kind of like weird. They haven't done that before.
yeah, so Corey's thesis wants to, instead of tilting or canting up, he wants to cant them down. And the program didn't want to do it. I think it's kind of late. So if they fail to do this, we can always say, we recommend this. No, we really don't want to fail. This is it's pretty fun missions.
How hard would it be to have variable canting rotors?
Oh, they don't want to do that. The thing about these things is, you kind of get stuck in like an over designing loop. And a variable canting rotor would probably add a lot of cost to weight. You increase the weight, then the skids, they have this like crazy, they have these crazy big skids. I don't know why they're so big. They're like twice the size of a helicopter on Earth. Because they have some weird requirement that it's gonna settle at some rate, and they're gonna absorb all the load in this extreme case. So then when you start adding a little bit of weight, the skids get really big. It's funny. Well, thank you all, I appreciate it.
Yes, thank you.
Okay, let's thank our speaker again.
Too late in
Yeah,
Stock up.
yeah, I was gonna say I will end the Zoom here, but please continue the discussion in the room.
Okay.
All right, thank you. Thank you, Michael. Thank you, Stella, for helping.